Hi everyone. So in the last lecture we were discussing countability. We have already seen countable set. This concept we have already seen the definition of countable set. Now in this lecture we will study what are uncountable set. Okay, so this is our topic for this lecture, that is uncountable set. So let's see what the definition of uncountable set. Uncountable set means a set is uncountable if and only if it is not countable. Yes or no? We have already seen the definition of countable set. So I can say a set is uncountable if and only if that is not countable. Yes or no? So tell me what this not countable means. When can you say a set is not countable? Let me know. When can you say a set is not countable? Tell me. You already know the definition of countable, right? The definition of countable set. What was that? If you remember, what was the definition of countable set? S is countable. S is countable if and only if size of S that is less than equal to size of N. This was the definition. So now you tell me the definition of uncountable. Now you tell me the definition of uncountable set. Tell me the definition of uncountable set. This is the definition of countable set, that S is countable if and only if size of S is less than equal to size of N. So tell me the definition of uncountable set. Uncountable set. When can I say S is uncountable? Uncountable means not countable. Uncountable, that means not countable. Okay, that simply means not countable. So when can I say S is not countable? Tell me. S is not countable if and only if size of S is strictly greater than size of N. Yes or no? Size of S is strictly greater than size of N. This is the definition of uncountable set. Okay, size of S that is strictly greater than size of N. So tell me, can I say uncountable set will definitely be infinite? Let me know. Can I say uncountable set will always be infinite? Yes or no? Yes, that will always be infinite. That will always be infinite because you already know that every finite set is countable. Every finite set is countable. So uncountable set will be infinite. And also you can notice the size of uncountable set. The size of uncountable set will be strictly greater than the size of natural numbers. Correct? This is the idea. Yes or no? Please tell me. Did you understand this? Very simple. So every uncountable set is infinite and the size of uncountable set is greater than size of natural numbers. This is the definition of uncountable set. So can I say that a set is uncountable if it is infinite? So when can you say? Tell me. This is my question. This is the simple question I want to ask you. Let's assume S is infinite set. An infinite set is uncountable. When can you say? An infinite set S is uncountable. When can you say? Tell me. An infinite set S is uncountable if and only if, let me know, if and only if the size of S is greater than the size of S is greater than N. And now what this means? Tell me what this means. Size of S is greater than size of N. What this means? This means I can say infinite set is uncountable if and only if there is no bijection. If and only if there is no bijection between N comma S. Between N comma S. Yes or no? Agree? Please tell me. Infinite set is uncountable if and only if there is no bijection between N comma S. Please tell me, did you understand? Because remember this point. Remember this point. If S is infinite, see, if S is infinite and there is bijection, if S is infinite, okay, and there is bijection, and there exists a bijection, then it will become what? And there exists a bijection between S comma N, then this S will become what? Then this S will become what? Then this S will be countable. Yes or no? Then this S will be countable infinite. Correct? Yes or no? So tell me, what is the definition of uncountable? When can you say a set is uncountable? An infinite set is uncountable if and only if there is no bijection between N comma S. Is this understood? Please tell me. Infinite set is uncountable if and only if there is no bijection between n comma s. This is the definition. So you can see this definition. So tell me, is this statement true or false? On your screen, assume set s is infinite, but there is no bijection between s comma n. But there is no bijection between s comma n. So tell me, can I say s is uncountable? Can I say s is uncountable? Yes, that will be uncountable. It cannot be countable, right? See, s is infinite. Already it is given to you. S is infinite. And there is no bijection between s comma n. So s cannot be countable, right? Yes or no? Agree? If this happens, then what I can say, then s cannot be countable. So s cannot be countable. So s is not countable. And not countable means uncountable. Not countable means s is uncountable. Okay, is this clear? Let me know. So this is the definition of uncountable set. Please understand this definition we will use many times. Okay, this is the final definition. This is the conclusion that if you have a set S, an infinite set S is uncountable if and only if. Okay, see, very simple. When can I say S is uncountable? When can I say S is uncountable? Set S is uncountable if and only if two things must happen. Two things must happen. First, S must be infinite. Okay, first S must be infinite, and what should happen? S must be infinite, and what must happen? There should be no bijection. There should be no bijection between S comma n. Okay, there should be no bijection between S comma n. This is the definition of uncountable set. In this situation, you will say that S is not countable. Okay, so this is the definition. So you can easily notice here, set A is uncountable if it is infinite and there is no bijection between A comma n. There exists no bijection between set of natural numbers and infinite set A. This is the definition of uncountable set. Okay, so this is the definition. You can notice set S is uncountable if and only if S is infinite and there exists no bijection between S comma n. Okay, this is the definition. Now let's see. Let's prove our first uncountable set. So far we have never seen any set which is uncountable. Yes or no? So far we have not seen any set which is uncountable. So far every set that we have seen that is countable. Now we will see our first uncountable set. This is what we are going to see. Our first uncountable set. And that is, and tell me one thing, if I can prove that some set is uncountable, then what it will tell you? It will tell you that there are different size of infinity. Yes or no? Yes or no? See what I'm saying. I'm simply saying that on the lowest level, you have set of countable infinite set. Okay. So if I can give you a set, if I can give you an infinite set, which is, I can say, whose size is more than size of natural numbers, then it means that different infinity, they have different size. Yes or no? Because this is the definition of uncountable. If you notice, this is the definition of uncountable set. S is uncountable. S is uncountable if and only if the size of S is more than size of n. Okay, yes or no? If and only if size of S is more than size of n. So that means some infinity are bigger than other infinity. Yes or no? That simply means some infinities are bigger than other. So I can say, can I say all the infinity have same size? Can I say all the infinite set have same size? All the infinite set, can I say they have same size? No. You can see some infinite set, they are bigger than other infinite set. For example, uncountable set. Okay, uncountable set means a set whose size is more than size of natural numbers. This type of set is called uncountable set. Okay, let's prove our first uncountable set. Let's see. I will start with real numbers. First, we will prove that set of real numbers is uncountable. Okay, this is what we are going to prove. Means set of real numbers, size of real numbers, size of set of real numbers, that is much bigger than size of natural numbers. So we are going to prove that real numbers are not countable. Set of real numbers that is not countable. Okay, let me tell you, this is the real line. Yes or no? This is the real line. This is the real line, 0, 1, 2, 3, and so on. Okay, this is the real line, correct? Now, what I am going to do, this is your real line. What I am going to do, notice, this is the real line. Now, I am going to prove that this is uncountable. Okay, this real line, this is uncountable, means the set of real numbers, the size of this set of real numbers, that is much bigger than size of natural numbers. This is what we are going to prove. Okay, we are going to prove the size of real numbers that is much bigger than size of natural numbers. This is what we are going to prove. Okay, let me tell you one interesting thing, that forget about all the real number. Of course, all the real numbers are there, but forget about them. If you just look at this range, this itself is bigger than n. If you look at this range, means if you look at this real numbers between 0, 1, if you look at real numbers between 0, 1, if you look at this range itself, this range itself is much bigger than size of natural numbers. If you look at this range, let me tell you, if you look at the size of this range, if you look at size of this range, this itself is much bigger than size of natural numbers. Okay, is this clear? Now, actually what we are going to do in this range also, see, very simple thing. In this range also, now this is your real line. This is your real line. This is your 0. This is your 1. This is your -1. This is your real line. Okay. Now, in this real line, I am saying that this range itself is bigger than the natural numbers. This range. Okay. Means the real numbers which are between 0, 1. Okay. Real numbers which are between 0, 1, that this size itself is bigger than set of natural numbers. And also what we are going to do, notice what we are going to do. Here we are only going to consider those real numbers in this range which contain only 3, 4. Okay, in this range what you do, just consider only those reals. Just consider only those reals. See, consider only those real numbers. Okay, in this range, consider only those real numbers which contain digits 3, 4 only. Okay, just consider this. This is simple point I am saying. I am saying that in this range, you consider only those real numbers in this range which contain digit 3, 4 only. Now let me tell you. This itself, if you look at this set, means real numbers which contain only 3, 4. Real numbers which contain only digit 3, 4. This set itself is bigger than set of natural numbers. Okay, now let's prove it. This is what we are going to prove. So tell me, did you understand what we are going to prove? We are first going to prove, this is our first point. We are first going to prove that the set of real numbers between 0, 1, that means in this range, containing only digit 3, 4, that is uncountable. We are going to prove this. So what we are going to prove, our set S is this. All the real numbers where x belongs to 0, 1. Okay, remember, x is a real number between 0, 1, and x contains only 3, 4. X contains only digit 3, 4. So first you understand this set. Then we will prove that S is uncountable. First you understand this set. Tell me which elements you have in this set S. First you understand this set S. Which elements you have in this set S? Give me some elements which are in this set S. Give me some elements. Tell me, this element, does it belong? 1.34, does it belong? This does not belong to S, because remember this point. In this set, we have those real numbers which are between 0, 1. Those real numbers between 0, 1 which contain only digit 3, 4. So can I say this belongs? Can I say this belongs to S? Can I say this belongs to S? Can I say this belongs to S? Again, this does not belong to S. Why this does not belong to S? Because if you look at this contains 0 also. Yes or no? This contains, if you notice, this contains, this is your 0.340000 and so on. Correct? Okay, so this also does not belong. So I hope you understood my point. Okay, so just understand this 0.34. This also does not belong to S. So what you have in S? Tell me. Is this clear? Which number belongs to S? So remember, in S, you have this type of points. For example, 0.3333 and so on. Yes, this belongs to S, right? Yes or no? For example, 0.33434433. For example, this also belongs to S, right? For example, 343434. This also belongs to S. Is this clear? Let me know. Did you understand which numbers belong to S? Did you understand this set? In this set, you have those real numbers which are between 0, 1, which contain only 3, 4. Only these digits, which contain only these digits, 3, 4. Okay. So what about 0.33? Does it belong to S? 0.33. Does it belong to S? No, it does not belong to S. It does not belong to S. Okay. So I hope you understood the set. Now, what we are going to prove? Prove that S is uncountable. Okay. What we are going to prove? Prove that S is uncountable. S is uncountable. First of all, you tell me, is this infinite set? I want to prove that S is uncountable. You tell me, is this infinite set? A simple question I'm asking. This set, is this infinite set? Yes, of course. Yes, of course, this is infinite set. Okay. You can keep creating. You can keep creating. Okay. So you can easily notice, you can keep creating. For example, 0.3333443444. You can keep creating, right? Yes or no? This also belongs to S. So you can keep creating. So you can see, first of all, this is infinite set. Now tell me, how to prove that S is uncountable? To prove S is uncountable, what I need to do? To prove S is uncountable. I want to prove S is uncountable. What I need to do? Tell me. I want to prove S is uncountable. Remember, S is already infinite set. S is already infinite set. I want to prove S is uncountable. So how to do that? To prove S is uncountable, you have to show that there is no bijection between S, N. Yes or no? To prove S is uncountable, show that there is no bijection. Show that no bijection is possible. No bijection is possible. No bijection is possible between N, S. Is this clear? Please tell me. Remember, S is already infinite set. If I can prove no bijection is possible between S, N, S, then can I say S is not countable? Tell me. S is already infinite set. If I can prove that there is no bijection possible between N, S, can I say S is uncountable? Yes, S will be uncountable, right? Okay, so this is what we are going to do. We are going to show that there is no bijection possible. Okay, we are going to show that there is no bijection possible. This is what we are going to do. I hope you understood. So for that, how to prove that? Tell me. I want to prove no bijection possible. No bijection possible between N, S. This is what we have to prove. We have to prove no bijection possible. What is coming to your mind? What should be our first step? This is what we have to prove. We have to prove no bijection possible. No bijection possible between N, S. There is no bijection possible. This is what we have to prove. So how to do that? Prove by contradiction. Yes or no? Prove by contradiction. Just prove by contradiction. Assume there is a bijection. Okay. What I will do? I will prove by contradiction. I am going to prove by contradiction. What I will do? I will assume there is a bijection. See, this is what I have to prove. Please understand. What I have to prove? I have to prove that no bijection. I have to prove that no bijection between N, S. Okay, how to prove? Prove by contradiction. You can prove it by contradiction. Okay. In prove by contradiction, what you will do? Please tell me. You can prove it by contradiction. What you will do? First, you will assume that there is bijection. Assume there is bijection. Assume there is some bijection. I don't know which bijection, but assume there is some bijection. Yes or no? I don't know which bijection, but assume there is some bijection between n comma s. Is this clear? Please tell me. Assume there is some bijection between n comma s. Then what you do? Then you bring a element. Okay, then this is what you do. See, first you assume there is a bijection. Now, if I can create, tell me a simple question I'm asking, please read this. Now, if I can create an element of S, an element, okay, if I can create an element X in S, okay, if I can create an element of S which is not covered by this bijection, which is not covered by this bijection, then can I say this bijection is not a bijection? Yes or no? Agree? Please tell me. See, bijection will cover every element or not? Let me know. If you have a bijection between two sets, it will cover every element or not? If you have bijection between two sets, bijection, one-to-one correspondence, if you have one-to-one correspondence between two sets, then that will cover every element of both the set. Yes or no? One-to-one correspondence, you have one-to-one correspondence, then that will cover every element of both the set. Now, if I can create an element of S which is not covered by this bijection, then can I say this bijection is not a bijection? Then this bijection is not a bijection. Yes or no? Then it is not a bijection. Then it is not a bijection. Is this clear? Then it is not a bijection. It means there is no bijection. Yes or no? So this is the overall idea. I hope you understood. Don't worry. It will be clear. But tell me overall this idea, did you understand what I'm saying? I'm saying that we have to prove that there is no bijection between n comma s. There is no bijection. So we can prove it by contradiction. First, we will assume there is bijection. We will assume some bijection, we will assume. Okay, I don't know which bijection. I will assume some abstract bijection. Some arbitrary bijection I will assume. Okay, I will assume some arbitrary bijection. Some arbitrary, okay, some abstract bijection I will assume. Then what I will do, if I can create an element of S which is not covered by this bijection, if I can create this type of element, then can I say it is not a bijection? Please tell me. If I can create some element which is not covered by this bijection, then can I say it is not a bijection? Yes, yes or no? So this is the idea. I hope you understood the idea. Now let's see the example. Let's see the proof. Now let's see the proof. Okay, can you take your copy pen? You can also take your copy pen. This is very interesting proof. Okay, so first what we are going to do, we are going to assume there is a bijection. Okay, so let's go step by step. Let's go step by step, one by one. So what we have to prove? First we have to prove. First let's write one by one. Okay, I will tell you everything one by one. So focus here. Remember, S is already infinite. S is already infinite. What we have to prove? We have to prove no bijection between n comma s. Between n comma s. There is no bijection between n comma s. This is what we have to prove. Okay, so what is the starting point? What is the starting point? We can prove it by contradiction. Prove it by contradiction. Okay, that is the starting point. We will prove it by contradiction. In this prove it by contradiction, what is the first point? First, we will assume there is bijection. Assume there is some bijection. There is some bijection. Okay, so first we will assume there is some bijection between n comma s. Between n comma s, there is some bijection. I will assume there is some bijection. Okay, some arbitrary bijection I will assume. I don't know which bijection, but I'm assuming some bijection. Some arbitrary, some abstract bijection I will assume. Some arbitrary bijection I will assume between n comma s. Okay, so let's assume that bijection is this. Okay, let's assume I am giving you that bijection. See, there is a bijection. So these are the set of natural numbers. This is your set S. I am giving you this bijection. 1, 2, 3, 4, 5. Okay, let's assume 1 is mapping to someone, yes or no? Because I am assuming there is a bijection. Agree? Yes or no? Please tell me. I am assuming there is some bijection. I am assuming there is some bijection F. There is some bijection F. Okay, so there is some bijection F. This is your bijection F. Okay, so if this is bijection, then there is one-to-one correspondence. Bijection means one-to-one correspondence, right? Yes or no? Okay, so I can say this one maps to some element. Okay, give me some random element, because I want a random bijection. See, I want arbitrary bijection. I want arbitrary bijection. So tell me, to which element this is mapping? Give me some element. Give me some element of S. For example, let's assume this is mapping to 4, 4, 3, 4, 3, 3, 3, and so on. Okay, let's assume this is mapping to this. Okay, please understand the set. In the set, you have only those real numbers between 0, 1 which contain 3, 4. So please understand the set S. Okay, so this let's assume 1 is mapping to this element. Let's assume 2 is mapping to this element, 3, 4, 3, 4, 3, 4, and so on. Let's assume 3 is mapping to this element, 3, 3, 3, 3, 3, and so on. Let's assume 4 is mapping to this element, 0.4, 4, 4, 4, 4, 4, and so on. Let's assume 5 is mapping to this element, 0.3, 4, 3, 3, 3, 4, 4, 3, and so on. Okay, are you getting my point? And so on. So like this, there is a bijection. Like this, there is a bijection. Is this clear? Is this clear? Please tell me. Like this, there is a bijection. Did you understand? Yes or no? First, I'm assuming there is a bijection. So let's assume this is the bijection. This bijection you have. Now what I will do? Now what I will do? Please tell me. Now what I will do? Now something interesting will happen. Now something very interesting I will do. What I will do? I will create an element. Okay, see, remember, this is the bijection I'm assuming. This is some arbitrary bijection. Okay, I'm assuming that there is bijection. Yes or no? We have assumed there is bijection. Assume there is bijection. Assume there is bijection F between n, S. So this bijection I have taken. This bijection I have taken. You can take any bijection. So assume there is bijection F between n, S. You can take any bijection. So let's assume this is that bijection. Now see what I'm going to do. Now I'm going to do something very interesting. I'm going to create element of S which is not covered by this bijection. Okay, what I will do now, we can create, I can prove it to you. We can create some element, at least one element I can create. We can create some element. Okay, we can create some element X belonging to S which is not covered by this bijection, which is not covered in this bijection, which is not covered in this bijection. A simple question I'm asking, if this is bijection, this must be onto, yes or no? Please tell me. If this is bijection, this must be onto. If this is bijection, this must be onto. So can I say every element of S must be covered? Can I say every element of S must be covered? Tell me. Remember, if it is bijection, it must be onto. Bijection is onto. You already know this. We know bijection is onto. Okay, bijection is onto and 1, 1. Onto and 1, 1. So you can notice that if you have a bijection like this, if you have a bijection like this, if you have this bijection, if F is bijection, then it must be onto. Then F is onto. Okay, so if F is onto, so every element must be covered. Agree or not? Every element of S must be covered or not? Tell me. Every element of S must be covered. Must be covered. Okay, now tell me, is this clear? Every element of S must be covered. Now what I am going to do? I am going to create some element, I am going to create which is not covered. If I can create this type of element, then will you agree with me that this is not a bijection? If I can create this type of element, then will you agree with me that this is not a bijection? Yes. And will you also agree with me that whatever bijection you create, that is not a bijection. Means whatever bijection you create, that is not a bijection. See, this is a random bijection or not? Did I take some specific bijection? No, I am taking some random bijection. You can take any bijection you want. You can take any bijection you want. Whatever bijection you will create, I will create some element which you have not covered. See, this is very simple game. Whatever bijection you create between n comma s, whatever bijection you create, I can create some element which you did not cover. Okay, so if I can create some element which is not covered by this bijection, then I can say this is not a bijection. Okay, how to create this type of element? Tell me. See, very simple. I will create this type of element like this. For example, notice here, you can notice, just look at this one. Here the first digit is 4, right? Yes or no? Here the first digit is 4, correct? So in this x, I will keep the first digit as 3. Okay, in this x, I will keep first digit as 3. Okay, I am creating x. Please notice, I am creating x. X is equal to the first digit I will keep as 3. The first digit I will keep as 3. Now tell me, whatever x I create, can I say that is definitely not this? That is not mapping to 1. Yes or no? See, whatever x I create, that is definitely not mapping to 1. That is not mapping to 1. Agree? Yes or no? Because I am changing this. I am changing this digit. Now what I am going to do? What will be my second digit? See, my second digit will be changed from here. I will create second digit from here. This is 4, so I will again make 3. My second digit will be 3. What will be my third digit? Now, first of all, you tell me, whatever I create, whatever x I create, can I say that is not mapping to 2? Can I say that is not mapping to 2? Whatever x I create, can I say that is not mapping to 2? Why? What is the reason? Because this and this, they are different. They are different in the second position. They are different in the first position. Okay, what will be my third digit? Notice, my third digit will come from here. Okay, this is 3. So in my x, I will put 4. In my x, I will put 4. Can I put 5? Can I put 5? Can I put 5? No, I want to create element of s. I want to create element of s. I want to create element of s. Remember, I want to create element of s. Please understand. I want to create element of s. Okay, so I will put it 4. Now tell me, what will be the fourth digit? Notice one more thing. Can I guarantee whatever x I create? Can I guarantee whatever x I create that is different from this, different from this, different from this? Yes or no? Agree? Yes or no? Whatever x I create, that will be different from this, different from this, different from this. I hope you understood. This x is different from this in the first position. In the first position. This x is different from this in the second position. And this x is different from this in the third position. Okay. Now what will be my fourth position? My fourth position will come from here. This is 4, so that will be 3. Now can I say this x is different from this number? Can I say this x is different from this number? Yes. Okay. What will be my next? The next will come from here. The next number, what that will be? The next will come from here. This is 3, so this will be 4. And so on, dot, dot. You understood, right? You understood this? Okay, and so on. I will keep putting. So first of all, you tell me. Okay, this x, does it belong to s? Because remember, I will keep doing this infinite. This is infinite, right? This is infinite. This is infinite. I will keep doing this. So tell me, do you agree with me that this x belongs to s? First of all, you tell me this simple point. This x, this belongs to s. Do you agree? Okay. And do you also agree that this x is not present in this bijection? Do you also agree that this x is not present in this bijection? Because remember, x is different from this, different from this, different from this, different from this, different from this. X is actually different from every number in this sequence. I can say that x is different from every number in this sequence, in this bijection? Agree? Yes or no? In this bijection, please tell me. Bijection, this x is different from every number. Okay, understood? Please tell me. So what I can say now? Now what I can say? So you can see x belongs to S, but x is not covered in this bijection. X does not have any pre-image. X belongs to S, but X has no pre-image. X has no pre-image in this bijection. In this bijection F. Okay, in this F. So can I say F is not a bijection? No pre-image in this F. So F is not a bijection. Yes or no? X belongs to S, but X has no pre-image in this F. So, okay. So X belongs to S, but X has no pre-image. X has no pre-image. Basically, you did not cover X. X has no pre-image in F. So F is not a bijection. So F is not a bijection, right? So F is not a bijection. Now you tell me a simple point. F is not a bijection. But did you understand this idea that whatever bijection you create, that will never be a bijection? Because you will create some bijection, I will create some X. Okay, please understand. So you can notice, remember F was arbitrary bijection, yes or no? Remember F was arbitrary bijection, correct? F was arbitrary bijection. Arbitrary, some random bijection I have taken. Remember F was arbitrary bijection. So if F is not bijection, okay, F was arbitrary bijection. So if F is not bijection, then can I say there is no bijection? So F is not bijection. We got contradiction. So if F is not bijection, there is no bijection. Then there is no bijection. Yes or no? Then there is no bijection. There is no bijection between N comma S. Okay, or you can understand like this, or you can understand like this, that whatever bijection you create, okay, see, this is what you can understand. You can understand like this: whatever bijection you create, what I will do, please tell me. It's like a game. Whatever bijection you create, what I will create, whatever bijection you create between N comma S, what I will create, tell me. I will create some X. I will create some X belonging to S which is not covered in your bijection. Which is not covered in your bijection, right? Which is not covered in your bijection. Whatever bijection you create, I will create some element X which is not covered in your bijection. So can I say no bijection exists? So no bijection exists, right? Yes or no? So no bijection exists between N comma S. Okay, so no bijection exists between N comma S, and hence what I can say, tell me. Hence S is uncountable. S is uncountable. Please tell me, did you understand this proof? Very interesting proof, right? See, very simple proof. Very simple proof. Okay, all you have to do, just please notice here what you have to do. See, very simple proof. See, we want to prove that S is uncountable. For that, what we need to do? See, notice here. Please focus here. We want to prove S is uncountable. For that, we need to prove that there is no bijection. We are proving by contradiction. First, we assume there is a bijection. Assume there is a bijection. Okay. Now, whatever bijection you will create, what I will do? Whatever bijection you will create, what I will do? I will create some element. I will create some element of S which you did not cover. Yes or no? I will create some element of S which is not covered. Correct? So whatever bijection you will create some bijection, and immediately what I will do, I will create some element x which is not covered in your bijection. Okay, which is not covered in F. So I can say that your bijection is not correct. Okay, so I can do this for any bijection. Whatever bijection you can create, I can always do this. So I can say there is no bijection. Yes or no? So I can say there is no bijection. So I can say this set S, this is uncountable. Okay, this set S, this is uncountable. Did you understand this? Please tell me. Let me know. Let me know, did you understand? See, whatever bijection you create, for example, let's assume you create this bijection. You might be thinking, sir, I will create some other bijection. Okay, you try that. For example, let's assume you create this bijection that, okay, 3, 3, 3, 3. And then let's assume you are creating this type of bijection. You are creating 3, 4, 4, 4, 3, 4, 4, 3, 3, 3, 4, 4, 3, 4, 3. Okay, like this, you are creating a bijection. Okay, are you getting my point? 4, 4, 3, 3, 4, 4, 4, 4, 4, 4, 4, 4, 4, 4. Okay, like this, you are creating a bijection. Is this clear? 3, 4, 3, 4, 4, 3, 3, 3. Like this, you are creating a bijection. Tell me what x I will create. Let's assume this bijection you have created. What x I will create? Let's assume you created this bijection. You created this bijection. Let's assume you created this bijection between n comma s. Okay, this bijection you have created, like 1 is mapping to this number, 2 is mapping to this number. Okay, this type of bijection you have created. Is this clear? 1 is mapping to this number, 2 is mapping to this number, 3 is mapping to this number, 4 is mapping to this number, and so on. So this bijection you have created. You created this bijection. Now tell me what I will do. Tell me what I will do. Let me know what I will do. Very simple. I will create a number like this. Notice. I will create like this. In this x, what I will do? I will do this. X will be point. See, here you have 3. So I will put 4. Why I am putting 4? Anyone want to tell me? Here you have 3. Why I am putting 4? So that this x is different from this. Yes or no? Agree with me? I am putting 4 here so that this x is different from this. Okay, this is what I'm doing. Now tell me, what will be second digit of x? What will be second digit of x? That will be 3. Why I'm putting 3? So that this x will be different from this. Different from this. So that this x will be different from this. Okay, next what I'm doing? Tell me. Next what I'm doing? What will be my next digit? Next digit of x? That will be 4. Why I'm putting 4? Why I am putting 4? So that this x is different from this number. This x must be different from this number. Okay. Next, what will be my next digit? What will be the next digit? The next digit will be 3. The next digit will be 3. Okay. Next, what will be my next digit? So you can see my next digit will be 3. And so on. Dot, 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 dot. And so on, right? Okay. Dot, 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 dot. So I have created this x. Can you notice this x belongs to S, but not covered in this bijection? Yes or no? This x belongs to S, but not covered in your bijection. But not covered in F. Okay. So this is the idea. I hope you understood. So finally, I can say whatever bijection you create, that will not be a bijection. Means whatever bijection you will give me, that is not a bijection. So I can say this is not countable. This set is not countable. Okay. And this proof, let me tell you, did you notice in this proof, did you notice we are getting a diagonal? In this proof, we are getting some kind of diagonal, right? Yes or no? This proof, if you notice in this proof, we are getting some kind of diagonal. We are going diagonally. Okay, we are going like this. See, in this proof, if you notice this diagonal, we are focusing on this diagonal. So because we are focusing on this diagonal, so this proof is actually called Cantor's diagonalization proof. This proof was given by Cantor. Let me tell you, And this is very interesting proof. Okay, you will find it very interesting. Don't worry, we will solve a lot of questions. But I'm telling you, this will become your favorite proof for whole life. Okay, very interesting proof. This is a very interesting proof technique, you can see. Okay, this is called Cantor's diagonalization proof, or I can say Cantor's diagonal argument. Okay, so this is a very powerful proof technique, you can see, very powerful proof technique, and very simple also. So this set is uncountable, and you can see, because we are focusing on this diagonal, you can notice we are focusing on this diagonal. So on this diagonal we are focusing, so this is your diagonal, right? So this method is called diagonalization proof. Okay, this is called proof by diagonalization, or I can say this is Cantor's diagonal argument, Cantor's diagonalization proof. Okay, understood? So this is what we have done, that this set S is uncountable. Please tell me, did you understand or not? Let me know. So this is your Cantor's diagonalization proof. So what we have done so far? Tell me what we did. What we proved. Tell me what we did. What we did. So let me tell you what we did. We did this, that if you see the real line, in this real line, if you notice, this is 0, this is 1, this is 2, and so on. Okay, -1, -2, and so on. Okay, now in this real line, if you notice, in this range, if you consider only those reals which contain 3, 4, that itself is uncountable. Just think about it. This range itself is uncountable. This range itself is uncountable. Yes or no? This range itself is uncountable. Okay, please tell me, this range itself is uncountable. So can I say your real line that will also become uncountable? Yes or no? This range itself is uncountable, means this itself has, if you see the size of this range, that itself is greater than size of natural numbers. If you see the size of this range, that itself is strictly greater than size of natural numbers. So this range itself is uncountable. So do you agree that the entire real line that will be uncountable? This range itself has size more than natural numbers, strictly more than natural numbers. So can I say the real numbers, the real line, that will also have, yes or no? So I can say set of real numbers that also has size of set of real number that is strictly greater than size of natural numbers. Is this clear? Please tell me. So set of real numbers is uncountable. So set of real numbers is uncountable. Set of real numbers. This set of real numbers, this is uncountable. This is not countable. Okay, means this infinite set, size of this infinite set is much bigger than size of this infinite set. This is what we have done. Size of this infinite set is much bigger than size of this infinite set. Is this clear? But remember, size of this infinite set is same as size of this infinite set. Okay, but remember, size of real numbers, that is much bigger than size of natural numbers. This is what we have proven. Did you understand the proof? Are you comfortable with Cantor's diagonalization argument? Let me know. Did you understand this? We will do a lot of questions, but so far, did you understand this proof? Let me know. The proof that we have seen. Is this crystal clear? The proof that we have seen. So this is your diagonalization method. You can read this. Just read this once. Cantor's diagonalization argument. Okay. See what this argument says. Notice what this argument says. Suppose we want to prove that infinite set S is uncountable. Then what you will do? Suppose we want to prove that infinite set S is uncountable. So what we will do? We will prove it by contradiction. First, we will assume it is countable. If it is countable, then there exists a bijection. Yes or no? So first we will assume that it is countable. If it is countable, then there exists a bijection. Now take arbitrary bijection. After taking arbitrary bijection, show that it is not a bijection. First you take arbitrary bijection, then you prove that it is not a bijection by creating an element of S which is not covered by this bijection. Okay. So first you take arbitrary bijection, then you prove that it is not a bijection by creating an element of S which is not covered by this bijection. Hence no bijection exists. Hence S is uncountable. Did you understand this? Please tell me this whole paragraph. Did you understand Cantor's diagonalization argument? This argument, did you understand? Let me know. Now let's see some more questions. Let's do some more questions. Prove that set of real numbers between 0, 1 that is uncountable. Okay. Now what we are going to prove? We are going to prove that this set, this entire set is uncountable. This is what we are going to prove. This entire set is uncountable. First of all, you understand this set. Let's call this set S. Let's call this set S. First, you understand this set S. In this set S, you have real numbers. X is real number and X is from 0 to 1. X is greater than 0, less than 1. This is your set. Is this clear? Now tell me, which elements belong to this set? First, you understand this set. For example, can I say 2.5, 2.53, this belongs to this set? No, this does not belong to this set. I am considering between 0, 1. Okay, so tell me, this element, does it belong? 0.01, does it belong to S? Yes, it belongs to S. Okay, it belongs to S. What about this 0.01, 01, 01 and so on? This will also belong to S. Correct? Okay, what about this 0.1111 and so on? This also belongs to S. Okay, what about this 0.1? This also belongs to S. Okay, what about this 0.3435098? What about this? What about this number? This also belongs to S. Okay, so I hope you understood. For example, 0.98, this also belongs to S. 0.99, this also belongs to S. So I hope you understood what is your set S. Did you understand the set S? Please tell me. Now let's prove. Now what we are going to prove? That this set S, that is 0, 1, all the real numbers, X is real and X is from 0 to 1. Okay, I am going to prove that this is not countable. We are going to prove S is uncountable. Prove S is uncountable. Okay, tell me one thing. This is what we want to prove. We want to prove that S is uncountable. What we need to do? If you want to prove S is uncountable, remember S is already infinite. Remember S is already infinite. S is already infinite. Now, how to say that S is uncountable? When can you say infinite set is uncountable? When can you say infinite set is uncountable? This will happen if and only if set S cardinality will be more than set of natural numbers. Okay, yes or no? Agree? Correct? Set S cardinality will be more than set of natural numbers. Okay, and when this will happen, see, this means there is no bijection. This means there is no bijection, right? This means there is no bijection between S, N. Correct? Okay, this means there is no bijection between S, N. So we need to prove. What we need to prove? We need to prove no bijection. This is what we need to prove. Remember, we need to prove no bijection between S, N. No bijection possible. No bijection possible between S, N. This is what we need to prove. So what I will do? I will prove by contradiction. Yes or no? I will prove by contradiction. Okay. So I will assume there is bijection. I will assume there is bijection. Yes or no? I will assume there is a bijection. There is some bijection, some arbitrary bijection you can take. I will assume there is some bijection between S, N. Between S, N. Okay, some arbitrary bijection I will take. So take some arbitrary bijection. Just take some arbitrary bijection. We don't know which bijection, but we are assuming there is some bijection. Okay, we are assuming there is some bijection F. Some bijection F. We are assuming there is some bijection F between S, N. Okay, if there is bijection, then what will happen? See, I am assuming there is some bijection. This is your N, this is your S, and I am assuming there is some bijection. Okay, this is 1, 2, 3, 4, 5, 6, and so on. This is your set of natural numbers. Okay, there is some bijection. Give me some bijection. Give me some one-to-one correspondence. Give me some one-to-one correspondence. Some one-to-one correspondence you give me. Give me some number here. Whatever your choice. Because remember, we are assuming that there is some bijection. We are assuming there is some bijection between S, N. This is what we are assuming. We are assuming there is some bijection. So give me one-to-one correspondence. Whatever you want, give me one-to-one correspondence. For example, you can give me, like someone is giving me 0.1123. What are the remaining numbers? Can I say automatically the remaining numbers will be 0? Can I say automatically the remaining numbers will be 0, 0, 0, and so on? Yes or no? Okay, automatically remaining numbers will be 0, 0, and so on. Give me some number here also. Please give me. Quickly. Give me some number here also. Give me one-to-one correspondence. Give me map of 2. What is the mapping of 2? Someone is saying 1, 2, 3, 4, 5, 0, 0. 1, 2, 3, 4, 5, and then 0, 0, 0, 0. Okay. What about the next? The next is 0.79045, then 0, 0, 0, and so on. Okay. You can also give me, okay, for example, maybe like this 0.143011111 dot dot dot. Yes or no? You can also give me, for example, maybe 0.99999 and so on. Okay, you can also give me, for example, 898977, okay, 9666666 and so on. Okay, like this. Okay, are you getting my point? You have given me some bijection. Now tell me what I will do. What is my purpose? Tell me what is my purpose. This is the bijection you have given. Okay, we are assuming some bijection, right? Assume some arbitrary bijection. Assume some arbitrary bijection. Just assume some arbitrary bijection F between N, S. Okay, we are assuming there is some arbitrary bijection between N, S. This bijection we are assuming. Then what I am going to do? Now what we do? Now we can create element. Now we can create some X. Okay, please understand. Now we can create some X belonging to S, which is not covered. Which is not covered. Which is not covered by F. I can create this type of element. Okay, I can create this type of element. So what I will do? See, I am creating this type of element which is not covered. What I will do? I just need to make sure that my X that is different from this entire sequence. Yes or no? I need to make sure. I want to make sure that my X that is different from this sequence, from every number in this sequence. So what I will do? What will be the first digit of my X? Tell me. What will be the first digit in my X? For example, this is 1. So you can put 2. Okay, you can put 2. See, this is not hard. I am putting 2. This is 1, so I am putting 2. Why I am putting 2? See, this is 1, so I am putting 2. So that this X is different from this. This my X is different from this number. That is the reason. Now, what will be the second digit of my X? What will be the second digit of my X? This is 2, so let's put 3. Just add +1. Okay, just add +1. Be consistent. Okay, don't do random. Be consistent. Just add +1. Okay, only add +1. Be consistent. Okay, so that there is no wrong. So that you don't do anything wrong. Tell me, what will be the next digit in my X? What will be next digit in my X? That will be 1. Okay, just add +1. Yes or no? Now tell me, so far, you tell me, whatever X I will create, can you guarantee that will be different from this number, different from this number, different from this number? Can I say, whatever X I will create, that is different from these numbers? Yes or no? You can notice, whatever X I will create, that is different from this number in the first position. Okay, whatever x I will create that is different from this number in the second position, and whatever x I will create that is different from this number in the third position. So whatever x I will create that is different from these numbers. What will be the next digit in my x? The next digit in my x, that will be again 1. Okay, just keep adding plus 1. What will be the next digit in my x? The fifth digit in my x. Fifth digit in my x. Okay, fifth digit, that will be 0. Just make it 0. Very good, very good. What will be the next digit in the x? What will be next digit in the x? The sixth digit, that will be 8. And dot, 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 dot. Yes or no? Dot. So, do you agree? Like this, I will keep doing. Like this, I will keep doing. Dot, 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 dot. Okay, dot, 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 dot. So, like this, I will keep doing. Correct? Okay, so tell me finally. First of all, you tell me this x, does it belong to? First of all, you tell me, does it belong to this s? This x, does it belong to s? Tell me. Simple question. Does it belong to s? Yes, it will belong to s, right? Yes or no? Please tell me. Understood? Yes, this will belong to s. And is it different from all the numbers in this sequence? So x belongs to s. X belongs to s, but not covered. But not covered by f. Correct or not? Can you notice this x? This is different from all the numbers in this sequence. Just look at this x. Okay, this x belongs to s. And can you notice this is different from all the numbers in this sequence? Okay, you can notice this x is different from every number in this sequence, in this bijection. Okay, is this clear? X is different. X is different from every number in this bijection. X is different from this number. X is different from this number. X is different from this number because of third position. X is different from this number because of fourth position. X is different from this number because of fifth position. Tell me, X will be different from this 100th number in which position? X will be different from this 100th number in which position? In the 100th position. Yes or no? So you can notice X is different from every number in this bijection. So I can say X is not covered. Yes or no? In your bijection, you did not cover X. Okay, so X belongs to S. X belongs to S, but not covered by S. Okay, not covered by X. So finally, what I can say, tell me. So I can say X belongs to S, but no pre-image. But no pre-image in F. So F is not bijection. Yes or no? F is not a bijection. And hence, can I say there is no bijection exist? Can I say there is no bijection exist? There is no bijection exist. Why there is no bijection exist? Because remember, this F was arbitrary, right? If you remember, this was arbitrary. This was arbitrary bijection. We took arbitrary bijection, we took. Okay. So for this arbitrary bijection, we have proved that this is not a bijection. And because this is not a bijection, so no bijection exists. And because no bijection exists, so S, that is 0, 1, this. So S is what? Tell me. So S is what? That is uncountable. That is uncountable. Is this clear? Again, did you notice we got the same? Which argument? This argument is called what? This argument, what this argument is called? This is called Cantor's diagonalization. This argument is called Cantor's diagonalization. Why? What is the reason? Because we are just following this diagonal, right? Yes or no? This diagonal we are following. So this proof is called Cantor's diagonalization proof. Yes or no? This is the diagonal, you can notice. So that is the reason this proof is called Cantor's diagonalization proof. I hope you understood. So I can say finally this set, which is all the real numbers between 0, 1, this set is basically not countable. This is what we have proved. Formal proof we have done. Okay. So I hope you understood. So now, do you agree that set of real numbers is uncountable? Please tell me. Do you agree set of real numbers is uncountable? Because remember, in the real numbers, if you take this gap, just look at this gap. This gap itself is uncountable. This gap itself is uncountable. This itself is uncountable in the real line. In the real line, this gap itself is uncountable. Okay, so the entire real line, that is uncountable. Entire real line, that is also uncountable. Okay, so remember, the size of this infinite set is much bigger than size of this infinite set. This is what we have proven. Did you like the proof? And this proof is called Cantor's diagonalization proof. Proof by diagonalization, or I can say Cantor's diagonal argument. Okay, this is what we have seen. I hope you understood this. Please tell me, did you like this proof? Let me know. This method, very simple, right? If you solve 2-3 questions, then this is much easier. This is very easy. Okay, so now we are going to do a lot of practice. So can you take your copy pen? Can you take your copy pen? A lot of practice we are going to do, and you will do it. Okay, I will give you the question, you try, I will also try. Okay, so let's do this. Now, what we are going to do, so far we have seen this Cantor's diagonalization argument we have seen, right? Cantor's diagonalization argument we have seen. Now, using that, we will prove more uncountable sets. Using that, we are going to prove more uncountable sets. Okay, so let's start with our first. This is very popular question. This is from MIT. You can see, you will find this question in every standard university. Okay, what this question is saying, tell me. This question is saying that let B be the set of all infinite sequences of 0, 1. Let B be the set of all infinite sequences of 0, 1. Prove that it is uncountable. Prove using proof by diagonalization. Okay, proof by diagonalization. The same question I can also say, prove that set of infinite length binary strings is uncountable. Okay, set of infinite length binary strings, that is uncountable. The same question has come in the TIFR exam last year. Okay, in 2022, you can see. The same question has come in the TIFR exam also. In this TIFR exam, you can notice, just see this TIFR 2022 question. They are asking what they are asking. See, they are asking that a binary string infinite, right? A binary string finite, infinite, and then basically they are asking, see, this statement they are asking, the set of all infinite binary strings is uncountable. So this question has come in the TIFR exam also. So this is a very, I can say, very popular standard question. Did you understand the question? Please tell me. Did you understand the question? The question is saying that set of all infinite length binary strings means this set, which set? This is set B, which is set of all infinite length binary strings. Okay, this W is infinite length. W is binary string of infinite length. W is binary string of infinite length. W is binary strings of infinite length. Now we need to prove that this set is uncountable. Now some of you might be thinking that string always has finite length. Is there anyone here who is thinking that, sir, string always has finite length? String cannot have infinite length. Please tell me, is there anyone here who is thinking that string always has finite length? String does not have infinite length. See, that is true only in theory of computation. Yes or no? Only in theory of computation that is true. In basic theory of computation, in the basic theory of computation course, in that course, we deal with only finite length strings. Correct? Agree? In our theory of computation course, in the basic theory of computation course, we deal with only finite length strings. So by default, in theory of computation, by default string means finite length strings. But I can define infinite length strings also. Yes or no? If I want, I can define it, right? Is there anyone to stop? Tell me. If I want to define infinite length strings, I can define that. Agree with me? In theory of computation, every string has finite length only. Okay, in our automata theory course, in the theory of computation course, in the basic TOC course, I can say we deal with finite length strings only. Okay, our strings are always of finite length. Okay, we don't have infinite length strings. All these machines that we study, like DFA, NFA, okay, PDA, Turing machine, PDA, Turing machine, okay, all these things like context-free grammar, okay, all these things that we have, okay, they basically, they deal with what? All of them, they deal with what? Tell me. All of them, they deal with finite length strings, correct? All of them, they deal with finite length strings. Okay, all of them. But remember, if you want, you can define. Actually, there is something called Bookie automata. This you will study in the advanced TOC. In the advanced TOC course. Okay, if you take TOC course in your MTech, in the advanced TOC course, for example, if you take this course in MTech, okay, so I took this course in the MTech in ISC Bangalore. Okay, so in this course, there is something called Bookie automata. This is advanced course. Don't worry about it. This is not a basic course. There is something called Bookie automata. Bookie automata. Let me tell you this Bookie automata. Okay, this Bookie automata, this deals with infinite length strings. This deals with infinite length strings. Infinite length strings. This deals with infinite length strings. Is this clear? So anyway, this is the simple point I'm telling you, that in our theory of computation course, in the basic theory of computation course, or I can say from the GATE exam point of view. Okay, so in the basic TOC course, every string has finite length. Every string, because all these machines, DFA, NFA, PDA, Turing machine, context-free grammar, all these things, they deal with finite length strings only. So our strings in our course, in theory of computation course, our strings, they have finite length. We don't have infinite length string. Yes or no? But anyway, the point is simple. The question here, you can notice, if you want to define, you can define. So let's see this question. Now let's prove this question. So you can see this is a very popular question. Now let's prove it. So tell me what we need to prove. We need to prove this set B, that is W, where W has infinite length. Remember, W is a binary string of infinite length. Binary string of infinite length. W is binary string of infinite length. Is this clear? So what type of strings we have in B? First you understand B. What type of strings we have in B? Tell me, this string do we have in B? Does it belong to B? Let me know. This string, does it belong to B? No. This string does not belong to B. Because remember, in this B, every string has infinite length. Every string that has infinite length. So for example, this string belongs to B, right? This string belongs to B. Okay, for example, this string belongs to B. For example, this string. This belongs to B. Okay, so I hope you understood. For example, 0, 1, 0, 1, 0, 1, 0, 1, and so on. This belongs to B. Okay, so I hope you understood what strings belong to B. Remember, this string does not belong to B. Okay, for example, 0, 0, this string does not belong to B. Okay, this string does not belong to B. Okay, so you understood the B. What is the set B? Now, what we need to prove? Tell me what we need to prove. We need to prove that it is uncountable. Okay, we need to prove B is uncountable. This is what we need to prove, that B is uncountable. First of all, is this B infinite? First of all, you tell me, is this B infinite? Yes, of course. You can create any number of strings. You can keep creating the strings. So yes, this B is infinite. This is an infinite set. Okay, we need to prove that this is uncountable. So tell me how to prove it. I want to prove this is uncountable. How to prove it? You can prove by contradiction. You can prove by contradiction, correct? Okay, let's prove by contradiction. What is the step number 1? Assume it is countable. That is the step number 1, right? Assume B is countable. Just assume B is countable. If B is countable, okay, remember B is already countable infinite. Okay, B is already infinite. So assume B is countable. So what will happen? Assume B is countable, and you already know that B is already infinite. You already know this. You know B is already infinite. Okay, so assume this is countable for contradiction. Remember this point. We want to prove B is uncountable. This is what we want to prove. So we will prove by contradiction. First, we assume B is countable. If it is countable, then what to do? Then what will happen? Then there exists a bijection. Yes or no? If this is countable, then there exists a bijection. Then there exists a bijection between n comma b. Correct? Okay. So now what to do? There exists a bijection between n comma d, n comma b. So this is what we are assuming. Okay. So let's assume this is the bijection. So remember, there exists a bijection between n comma b. So take a bijection. Okay. So this is the simple point. Remember, we are assuming this is a proof by contradiction. Okay. Just one time I am writing so that you become very familiar with all these things. We need to prove B is uncountable. This is what we need to prove, that B is uncountable. Okay. And what we will do? We will prove by contradiction. This is what we will do. We will prove by contradiction. Okay. This is what we are going to do. Now, what is the first step? First step is assume assume B is countable. This is your first step, that assume B is countable. Now, you already know B is infinite. You already know B is infinite. So if B is countable also, then what will happen? Then what will happen? Then there exists a bijection. Okay, there exists some bijection between n comma b. There exists some bijection. So what you do? What is the step number 2? Take arbitrary bijection. Yes or no? What is the step number 2? What is the step number 2? Take arbitrary bijection. Take arbitrary bijection between n comma b. Okay, take some random bijection. Take some arbitrary bijection between n comma b. Okay, so just take it. So tell me, let's assume you have this bijection you take. This is your set n. This is your set b. I am giving you a bijection. I am giving you a bijection f. Let's assume this f is bijection. Okay, I am assuming this f is bijection. 1, 2, 3, 4, 5, 6, and so on. And okay, so give me one-to-one correspondence. Please give me one-to-one correspondence. Because I am assuming there is a bijection. There is a bijection between n comma b. This is what I am assuming. Okay, so take arbitrary bijection between n comma b. Take arbitrary. So give me some bijection. Whatever bijection you want, you can give me. So give me the mapping of 1. Let's assume 1 is mapping to 0, 0, 1, 1, 1, 1, and so on. Okay, let's assume 1 is mapping to this. Let's assume 2 is mapping to 1, 0, 1, 0, 1, 0, 1, 0, and so on. Okay, 1, 0, 1, 0, and so on. Okay, let's assume 3 is mapping to 0, 0, and so on. Okay, 3 is mapping to 0, 0, 0, and so on. Okay, let's assume 4 is mapping to, and so on. Okay, let's assume 5 is mapping to 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, and so on. Okay, something. So like this. Okay, let's assume 6 is mapping to 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1. Okay, something. So like this. Okay, this is the bijection you have. Is this clear? You have given me a bijection. This bijection, we have taken arbitrary bijection. This arbitrary bijection I have taken. Okay, what I have taken? We have taken arbitrary bijection. We have taken arbitrary bijection f between n comma b. Okay, now what is your next step? What is our next step? Now what we will do? Now I will create some element of b which does not which is not covered in this bijection. Yes or no? Now we can create, see, very interesting. Now we can create some element x in this set b which is not covered by f, which is not covered by this bijection f. If I can create this type of element, tell me. If, see, you are saying this is a bijection. This is what you are saying. You are saying this is a bijection. Now, if I can create some x which is not covered, if I can create some element of b, which you did not cover here, then can I say this is not a bijection? Then can I say this is not a bijection? Yes. Yes, this is not a bijection. And remember, this is arbitrary bijection. because this is arbitrary bijection. And for this arbitrary bijection, if I say this is not a bijection, if I prove this is not a bijection, then that means there is no bijection. For this arbitrary bijection, if I prove this is not a bijection, then I can say there is no bijection. Okay, so tell me, how will you create that element? I want to create element X. How will you create that element X? Very simple, very simple. See, in my element X, what will be the first symbol in my element X? Here you have 0. Here the first symbol is 0. So in my element X, first symbol will be 1. Okay. Why I am putting 1 here? So that my element X is different from this number. Yes or no? Agree with me? Why I am putting 1? Okay, this symbol, putting this symbol, first symbol 1, so that my X, that is different from this element. Okay, this is what I'm doing. So my first element will be 1. What will be my second element? Here the second element is 0. My second element will be 1. Okay. Next, what will be my third element? Here the third element is 0. My third element will be 1. Okay. What is my fourth element? Here you can notice fourth element is 1. My fourth element will be 0. Okay. Next, what will be my fifth element? Here the fifth element is 0. My fifth element will be 1. Next, what about the next? Here, what is the sixth element? The sixth element is 1. My sixth element will be 0. Okay, my sixth element will be 0. Is this clear? And so on, dot, 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 dot. Okay, and so on, and so on. So can I say, tell me, like this I will keep doing, like this I will keep doing. First of all, you tell me, is this an infinite length string? This X that you will get, can you guarantee it has infinite length? Can you guarantee this X has infinite length? How? How can you guarantee? How can you guarantee X has infinite length? Because this is an infinite sequence. Yes or no? This is an infinite sequence. Agree or not? See, how can you say this X is infinite? How can you say this X has infinite length? Because this is an infinite sequence. Because this is an infinite sequence. Correct? Yes or no? Because this is an infinite sequence. You can easily notice this is an infinite sequence. This is an infinite sequence. So I can say my X is also infinite. And you can notice X is binary string. So X is infinite binary string. This is binary string of infinite length, right? This is binary string of infinite length. This is binary string of infinite length. What that means? This is binary string of infinite length. What that means? So X belongs to B. So X belongs to B. Remember, this X belongs to B. But tell me, this X is different from all the numbers in this sequence. See, this X is different from this number because of first position. This X is different from this number because of second position. This X is different from this number because of third position. This X is different from this number because of fourth position. So X belongs to B. X belongs to B, but X is different from every number in this sequence. Correct? Agree? Okay. So notice. So remember, X belongs to B, but X is not covered in this sequence. X is not covered by F. Correct? Okay, X belongs to B, but X is not covered by F. I can also say that X belongs to B. Okay, and X is different from all the numbers in this sequence. In this sequence. Okay, X is different from all elements in this sequence. In this sequence. So you did not cover X. Can I say? So you did not cover X. So I did not cover X. So finally I can say that X belongs to B, but no pre-image for X. Yes or no? But there is no pre-image for X. You did not cover X, but there is no pre-image for X in F. Okay, you did not cover this X. So I can say that F is not bijection. Yes or no? Correct? So F is not bijection. And because remember, F was arbitrary. Remember, F was arbitrary bijection. If you remember, we took arbitrary bijection, we took. Okay, this was arbitrary bijection. For this, we are saying that F is not a bijection. So what that means? So what that means? So that means there is no bijection. Yes or no? So no bijection exists. So no bijection exists between N comma B. And hence what I can say, tell me. Hence what I can say. Hence B is uncountable. Hence B is uncountable. That's it. This is your proof that set B is uncountable. Did you like this? Please tell me. I hope you enjoyed all these proof and all these things. So you can see the set of all infinite length strings, the set of all infinite length strings, that is uncountable. That is uncountable. Okay. So did you like the proof? All these, are you finding these interesting? Please tell me. Did you find all these proof? These are very interesting and very easy. Quite easy. Okay, let's move on now. Now let's see this question. This is actually gate exam question. Right now we will only solve the part R. In this gate exam question, in this gate 2018 question, okay, let's solve this R. That is set of all functions from n to 0, 1. Let's solve this. Is this countable or uncountable? What we are going to do? This is what we are going to do in this gate exam question. You can see this is a gate exam question. Question number 27, gate 2018. You can see. Okay. Now, prove that set of functions from n to 0, 1 is uncountable. Prove that set of functions, remember, now what is your set? Set of functions from n to 0, 1, that is uncountable. This is what we need to prove. Is this clear? We need to prove that set of functions from n to 0, 1, that is uncountable. First, you understand this. Okay, what is your base set? Tell me. What is your base set? That you tell me. What is your base set? Your base set is set of functions, right? Yes or no? Your base set. You have a set of functions. F is a function. F is a function. From n to 0, 1. Okay, F is a function from n to 0, 1. Is this clear? Please tell me, did you understand this? That F is a function from n to 0, 1. Okay, you understand this set. In this set, which type of elements you have? For example, in this set you have functions from n to 0, 1. Functions from n to 0, 1. For example, notice. For example, this is a function from n to 0, 1. Consider this. This is a function, like, for example, consider this F1. Okay, from n to 0, 1. 1, 2, 3, 4, 5, and so on. Okay, so can I say this is a function, like, for example, if I do like this? Yes or no? And so on. Do you agree? So you can see this is your function. This is a function. Okay, this is a function like this. So you can see, tell me, because this is a function from n to 0, 1. So this F1 belongs to S. Yes or no? So this F1 belongs to S. I hope you understood. So you can see this F1 belongs to S. This function belongs to S. Please tell me, did you understand? Did you understand what you have? What is your base set? What is your base set? Remember, in your base set, you have functions like F1, F2, F3, F4. Your functions. Each of them is a function. This is a function from this is a function from n to 0, 1. Each element is a function. For example, I don't know, but maybe F3 is this. Maybe F3 is this. 1, 2, 3, 4, 5. Maybe F3 is this. That all are mapping to 0. It can be F3, right? Is this a function? If everyone is mapping to 0, is this a function? If everyone is mapping to 0, is this a function? If everyone is mapping to 0, yes, this is also a function. No problem. Okay, no problem. This is also a function. So maybe this is the F3. Maybe this is F3. So you can notice F3 also belongs to set. F3 also belongs to our set S. Okay, you can notice. So like this, I hope you understood. Now tell me, how many such functions you can create? From n to 0, 1, how many functions you can create? Tell me, from n, this is your set n. This is infinite set, 1, 2, 3, 4, and so on. From n to 0, 1, how many functions you can create? Let me know. How many functions you can create? Tell me. Infinite number of functions. You can create any random function you can create, for example. Yes or no? Infinite number of functions you can create, correct? Agree or not? Okay, so you can see how many functions are possible. Tell me. So this, I can say this set, if you notice this set, where f is a function, where f is a function, where f is a function, f is a function from n to 0, 1. How many such functions you can create? Tell me. How many such functions you can create? Okay, because this n is infinite. Okay, how many such functions you can create? I can say this is infinite. Infinite number of functions you can create, correct? Because this n itself is infinite. So from n to 0, 1, you can create infinite number of functions. You can create random functions. For example, maybe this type of function you can create. Okay, some random function you can create. So this is an infinite set. Is this clear? Please tell me. Okay, now let's prove that this S is uncountable. What we need to prove? We need to prove that S is uncountable. This is what we need to prove, that this set of all functions, this set of functions, in this set you have functions, we need to prove this S is uncountable. So what we will do? We will prove by contradiction. Please take your copy pen. If you can, please take your copy pen. Let's prove by contradiction. What the first step? I want to prove that S is uncountable. This is what I want to prove. So I will prove by contradiction. So I will assume S is countable, right? Yes or no? I will assume S is countable. So let's assume S is countable. Now tell me, if S is countable and you already know S is infinite, you already know S is infinite, S is countable infinite, that means what? S is countable infinite, that means what? That means there exists bijection. That means there exists bijection between n comma s. Between n comma s there exists a bijection. So take a random bijection. Okay, there exists a bijection. So what you will do? There exists a bijection. What will be your next step? So take arbitrary bijection. Take arbitrary bijection. Is this clear? What you do? You take arbitrary bijection. So for example, this is your set and this is your set S. I am giving you arbitrary bijection. 1, 2, 3, 4, 5, 6, and so on. And this is arbitrary bijection I have given to you. So tell me, in this S, what is the element? Tell me, what are the elements of S? Tell me, what are the elements of S? Elements of S are the functions. Yes or no? Elements of S, these are the functions. In S, you have functions. Yes or no? These are the functions. Functions are the elements. Okay, yes or no? So now I am saying that there exists a bijection. So take arbitrary bijection. Take arbitrary bijection. Okay, so give me a bijection. Anyone want to give me a bijection? For example, this one is mapping to some function. Let's call it F1. I don't know what is F1. Do I know what is F1? Do you know what is F1? What is F1? No, F1 can be anything. Okay, F1 can be anything. I'm calling it F1. Means whatever function you assign to 1, I'm calling it F1. Did you understand what I'm doing? Whatever function you assign to 1, I will call it F1. Whatever function you assign to 2, I will call it F2. Whatever function you assign to 3, I will call it F3. Whatever function you assign to 4, I will call it F4. That is your choice. Whatever function you assign to 5, I will call it F5. Like this. Okay, is this clear? So like this bijection I have taken. I have taken this bijection. Now what is my task? So remember, I have taken this arbitrary bijection. Please notice. I have taken this arbitrary bijection. I have taken bijection F. Okay, I have taken arbitrary bijection F between n comma s. Okay, this arbitrary bijection, maybe I can call it G. Arbitrary bijection G I have taken. I have taken arbitrary bijection G between n comma s. This is what I have done. Okay. Now what I will do? Please tell me now what I will do. I will create a function which is not appearing here. Yes or no? Now what I will do? Now we can create a function. Now we can create a function h. Now we can create a function h which does not appear in this bijection. Which does not appear in this bijection. Okay, now what we are going to do? Now we can create a function h which does not appear in this bijection. Tell me how to do that. I want to create a function f. I want to create a function h which does not appear in this bijection. Which does not appear in this bijection. I want to create a function h which does not appear in this bijection. This function h I want to create. Please understand. I want to create a function h. Okay, so this function h I want to create. I want to create a function h 1, 2, 3, 4, 5, 6, and so on. I want to create a function h which does not appear in this bijection. How to do that? Anyone? Anyone want to help? This h must be different from f1. What to do? I want to make sure h and f1 are different. How to do that? I want to make sure that h is different from f1. I want to make sure. Then how to do that? Anyone? Any idea? I want to make sure h is this new function I am creating. This function is different from f1. See what you can do. You can just check where in this f1 where 1 is going. Yes or no? In this f1 where 1 is going. In this f1, let's assume 1 is going to 0. Let's assume in this f1 1 is going to 0. Then in this h what you will do? Please understand. Let's assume in this f1 1 is mapping to 0. This f1 is a function, right? Agree? This f1 is a function from n to 0, 1. Okay, let's assume in this f1 this 1 is mapping to 0. So in this h what this 1 will map? So this h will map to, in this h this 1 will map to 1. Understood? Now can I say h is different from f1? Now can I say h is different from f1? Yes, h is different from f1, right? Now, okay, so very simple. H is different from f1. Now make sure that h is different from f2 also. Okay, now make sure h is different from f2 also. How to do that? I want to make sure that this is different from f2. Let's assume f2 is like this. Okay, let's assume f2 is like this. See, let's assume your f2 that was like this. Let's assume in your f2 1 is mapping to 0. Then what you will do? Let's assume this is your f2. This is your f2. Okay, so tell me, in your f2 1 is mapping to 0. Now what you will do? In this h what you will do? Sorry. In this f2 you focus on 2. In this f2 you focus on 2. In this f2 you just focus on where 2 is going. See, in this f1 we were focusing on 1, where 1 was going. In this f2 you focus on where this 2 is going. Let's assume 2 is going to 0. Then in this h where 2 will go? In this h 2 will go to 1. Yes or no? In this h 2 will go to 1. Okay, so we got this. In h 2 will go to 1. Okay, now what we need to make sure? We need to make sure h is different from f3. How will you make sure that? H is different from f3? See, maybe f3 is like this. 1, 2, 3, 4, and so on. Okay, 0, 1. This is your f3. Okay, this is your f3. Maybe in f3, on which element I will focus? In f3, on which element I will focus? I will focus on 3. Let's assume 3 is going to 1. Then in h what will happen? Then in h what I will do? In h 3 will go to 0. Yes or no? in H, 3 will go to 0, correct? And so on. I hope you understood. So you can notice H is different from F1, H is different from F2, H is different from F3. And let's assume in this F4, okay, just for a moment, let's assume that in this F4, let's assume 4 is mapping to 0. Let's assume 4 is mapping to 0. Then tell me where this H will map for. In this H, 4 will map to 1. Okay, let's assume in this F5, 5 is mapping to 1. 5 is mapping to 1. Then in this H, where 5 will map to 0. Okay, let's assume that in this F6, let's assume in this F6, 6 is mapping to 1. Then tell me in this H, what will happen? In this H, what will happen? In this H, 6 will map to 0. In this H, 6 will map to 0. Yes or no? 6 will map to 0. And so on. Did you understand this simple? I hope you found this interesting. Please tell me. Did you understand the question? What is the set? The set is set of functions. Yes or no? Your base set. That is set of functions from n to 0, 1. Now, we are assuming there is a bijection. We assume there is a bijection. Okay, so let's assume this is the bijection. Now we are creating a function h, which is different from all of them. For example, in this F1, let's assume 1 is mapping to 0. Then in this H, 1 will map to 1. In this F2, let's assume 2 is mapping to 0. Okay, then in this H, 2 will map to 1. In this F3, let's assume 3 is mapping to 1. Then you can notice in this H, 3 will map to 0. And so on. You will keep doing like this. So finally, can I say, this H that you have created, tell me, simple point I'm asking, this H that you have created, this is a function or not? This H, is this a function from n to 0, 1? Let me know. This H that you have created, focus on this H. Is this H a function from n to 0, 1? Yes, this is a function. This is a function from n to 0, 1. So can I say that H belongs to S? So can I say H belongs to S? So can I say H belongs to S? Because remember, because H is a function. H is a function from n to 0, 1. So I can say H belongs to base set S. Correct? Yes or no? So I can say H belongs to, because H is a function from n to 0, 1. So H belongs to S. But did you notice that H is different from all Fi? F is not same as Fi for all I. Yes or no? For example, H is different from F1, H is different from F2, H is different from F3, H is different from all of them. Yes, correct. H is different from all of them. Means this H, this does not appear in this sequence. So I can say, but I can say H is not covered in the arbitrary bijection. In the arbitrary bijection that we took. Arbitrary bijection G. Okay, we took arbitrary bijection G, right? We took arbitrary bijection G. This was our arbitrary bijection G. Okay, we took arbitrary bijection G. In this arbitrary bijection G, remember, this arbitrary bijection G we took. In this arbitrary bijection, I can say that H does not appear. So this is what I'm saying. So H is not covered in the arbitrary bijection G. So G is not a bijection. So G is not a bijection, right? So G is not a bijection. So there is no bijection, right? Because this G was arbitrary bijection. So there is no bijection. So there is no bijection between set of natural number, comma S. Hence, S is uncountable. So from here you can say S is uncountable. This is your proof. This is the proof. So please tell me, did you like this proof? Did you understand this question? Let me know. This was your GATE exam question. You can see. This is your GATE exam question. So please notice, this is your GATE 2018 question. Question 27, part R. What was the question? The question was set of functions. Set of functions from where to where? Set of functions from n to 0, 1. Set of functions from n to 0, 1. Set of functions, remember. This was the question. The question was set of functions from n to 0, 1 is uncountable. This set is uncountable. Did you understand this proof? Let me know. So remember, your proof is actually very simple, because if you notice your set, that is set of functions. In your set, you have functions f1, f2, f3, f4, and so on. You have functions. Okay, each fi is a function, remember. Every fi, that is a function from n to 0, 1. Okay, every fi. Here you can notice. This fi, this is a function from n to 0, 1. Okay, so this was a function. And now we are saying we have proved that this set of functions, this is uncountable. This set is uncountable. And the proof is very simple. First, you assume this is countable. Okay, you assume this is countable. If this is countable, then there exists a bijection with set of natural number. You take some arbitrary bijection, and then you create a function which is not covered in this bijection. You create a function which is not covered in this bijection. Okay, clear? Let me know. So the proof was actually quite interesting. So first you assume this is countable. First you assume this is countable. If this is countable, then there exists a bijection, right? Yes or no? If you assume this is countable, if you assume this was countable, then there exists a bijection. Then there exists a bijection. This type of bijection is there. Correct? Then there exists a bijection. Okay. Now you take this bijection G. Now what you will do? Now you will create a new function. So you take arbitrary bijection, this arbitrary bijection you have taken. Now you will create this new function. So notice what we did. We took arbitrary bijection. Please understand. We took arbitrary bijection G. We took arbitrary bijection G between n comma s. Okay, now what we are doing? Now we are creating a new function. Okay, now what we are doing? Now we can create. Please notice. Now we can create a new function. A new function h from set of natural numbers to 0, 1. Okay, I can create a new function h which is not covered by this bijection. Which is not covered by this bijection G. By this G, or I can say. Okay, which is not covered by this G. So you can see how to create this h. I want to create h. Okay, how to create this h? Tell me. This h I want to create. I want to create this new function h I want to create. So how to create this h? The idea is very simple. For example, in this f1, let's assume 1 was mapping to 0. Okay, 1 was mapping to 0. Then tell me, in this h what will happen? In this f1, let's assume 1 was mapping to 0. 1 was mapping to 0. Then in this h what will happen? Please tell me. Assume 1 was mapping to 0. Then in this h what will happen? 1 will map to 1. For example, in this f2, let's assume 2 was mapping to 0. Then what will happen? Then in this h what will happen? 2 will map to 1. In this f3, let's assume 3 was mapping to 0. Let's assume 3 was mapping to 0. Then in this h what will happen? 3 will also map to 1. Let's assume in f4, 4 was mapping to 1. 4 was mapping to 1. So in this h what will happen? 4 will map to 0. Let's assume in this f5, 5 was mapping to 1. Then in this h what will happen? 5 will map to 0. And so on, and so on. So like this, and so on, dot, dot. So you got this h. Now you can notice this H is not covered in this G. Okay, this H belongs to S, but not covered by G. But not covered by G. Okay, so I can say this G is not a bijection. This G, this bijection that you took, this is not a bijection. So no bijection exists. So this set S, this is uncountable. Let me know, is this clear? Did you find this interesting? Let me know. These are easy. All these things are very easy. This is your Cantor's diagonalization proof. Please tell me, is everything clear so far? Let me know. Let me know. Are you confident that if I give you some question, you can solve it? If I give you some question to prove that some set is uncountable, then can you solve it? I hope you found this very interesting. This is quite interesting, you can see. So can I give you this question as a homework? See this question, can I give you this question as a homework? This question is taken from MIT. A very nice question. Can I give this question as a homework? We will discuss it in the next session. Okay, so take this question as a homework. This is a very nice question from MIT. What this question is saying? You can see f is a decision function. It is mapping what this function is doing. As f, remember, a function is decision function. A function is decision function. It maps finite length bit strings to 0, 1. Okay. Let f be the set of all decision functions. Then prove that this f is uncountable. Okay, so read this question, understand this question, what this set f is. Okay, understand what is your base set, what we need to prove, and then you prove it. Can you do that? Take this as a homework. This is a nice, see, this is a nice question from MIT, very nice question. Take this as a homework. I have full confidence on you. You can do it. Okay, you can do it. So read this question, understand this question, and solve this question. Okay, so this is what we have seen. We have seen Cantor's diagonalization proof. This is what we have seen. Cantor's diagonalization method, proof by diagonalization. Did you find it interesting? Please tell me in the comments. Okay, please tell me in the comments if you find this interesting. So I have explained it to you. I hope you found this interesting. This is very interesting topic. Now, in the next lecture, what we will do? In the next lecture, we will see 3 definitions of countable set. We will see theorems of countable set, like union of countable set, intersection of countable set, cross product of countable set. Okay, all these things. So we will see 3 definitions of countable set, theorems of countable set, and we will see Cantor's theorem. Cantor's theorem we will see. This theorem we will use to create infinite levels of infinity. Basically, I will give you the proof that there are infinite levels of infinity. This proof I will give you. Okay, I will give you the proof that there are infinite levels of infinity. This proof is called Cantor's theorem. On this Cantor's theorem, there are 2 gate questions, 1 TIFR questions. Okay, so this we will see, and a lot of practice we will do in the next session. So in this session, I hope you found this session very interesting. This was the topic, Cantor's diagonalization proof. Please tell me, did you find this session interesting? Let me know. All these questions, all these proof, these are very simple. Just work it out. Okay, I'm sure that if you do these proof yourself, okay, just try. If you do these proof, if you do them yourself, then you will feel a lot of confidence. You will feel, and also I can guarantee that this will become your favorite topic. This diagonalization, this proof technique, you can see proof by diagonalization. This will become your favorite topic. Okay, so thank you everyone. See you tomorrow. Okay, the next lecture will be tomorrow. Okay, so tomorrow we will study these things. This is the agenda for tomorrow. Okay, thank you everyone.